Oh, make sure, don't forget, right now your hands out. If you have money, guys, for next week.
I did X-ray too, right?
Thinking by the way.
Yeah.
You're all right, dude.
That's what I was going to say. We all have it right now.
Go through and fill it out later.
Yes.
All right, the X-ray room, the X-ray tube itself is supported in many different ways. It could be a ceiling support system or floor support system. A ceiling support is more maneuverable and more you can manipulate the X-ray tube in any direction. It is suspended on. There's a couple of beams that's attached on the ceiling, which connect to like a telescoping device and can move the X-ray tube in any direction in the room, which is very convenient when you do your X-ray. Floor support is very limited to where you can manipulate your X-ray tube. Sometimes you could only go back and forth with a floor supporting system. There's a rail underground, just like some sort of attachment. You can only move the tube back and forth. Other tube, fluoroscopy tube, for example, is built underneath the X-ray table. So when you use a floor procedure, the floor or X-ray tube is built within a mobile device called CR. And the reason why it's called CR because it's shaped like a C. Very technical of us. And we use that mainly in a lot of procedure, especially in surgery. It's a big portable device you take into the surgery room, and they put a cover on it for sterilizations, and then you do your floor procedure. These are the images, ceiling and versus floor support. Again, the ceiling X-ray tube is supported some sort of something. As mentioned, like a telescoping device, just go up and down, and then you can move it in any direction. Whereas the floor mounted, you can always slide back and forth. It goes into an internal way you can manipulate the X-ray tube.
Does the X-ray tube on the floor one, does it move outwards and inwards too, or?
It does move outward, inward.
But like the X-ray tube, does it move like out, like sideways and then back, or no?
You can swing it.
Oh, okay.
But you can't, like, if you like the patient move somewhere, you can't move it. It's very limited. This type of system support mainly for upright chest X-ray. The gel when I work in is like this. It doesn't go anywhere. You just go back and forth. But it's usually for chest X-ray. It's a standard 72 inches. So I don't really move to it up. I just move it up and down to adjust the height. That's pretty much it. And everything else, it just stays the same. And this is mainly used for like limited room where the space is limited. Small picture of the four tube ceiling suspensions. Like a telescoping. I think I showed you this image before. The two things you notice most when you walk into the X-ray room would be the X-ray table and the X-ray tube. And usually the exposure area is in this same room, but there's a dividing area to prevent from scattering radiations reaching you. And there's usually a window that's that line, so you can see the patient during the exposure. Top of X-ray tubes. Tube can be built completely encased in the metal or in a pilot glass envelope. This is why I see mostly common, but a lot of tubes go into metal. And they call it glass envelope, even though it's no longer glass, it's just an envelope. This is a diagram of the X-ray tube itself. The tube connected to the collimations with the lights to represent the X-ray. It's coming out from the tube, the anode. It's radiating out and interacting with the patient. Okay, tube constructions. Again, this is just basic review from 146. This is where we cross paths. The basic component of the tube construction will be the housings where they place the extra tube inside the metal housing. Sometimes called tube assembly or just housing. And then we have a envelope. And this envelope is usually, depending on what kind of manufacturer, it could be glass or just metal in case. Here I have a picture of a glass vacuum envelope. And then of course the inside the envelope would be the cathode and the anode side. That's where the production of X-rays occurs. Okay, the housing. Tube housing is designed to protect and control excess radiation and electrical shock. The housing control any where the X-ray comes out. The only part where used for X-ray beam should come out will be the window or the port. That's where it should come out. Any place that the X-rays exiting besides the window or the port would be referred as leakage radiation, and we don't want that. Leakage radiation or radiation that escapes other than the window. By regulation, the tube cannot emit more than 100 milliroentgen per hour at a distance of 1 meter with a 75 to 80 kV setting.
Can you repeat that?
By regulations, the liquid radiation cannot be more than 100 milliroentgen at a distance of 1 meter with a setting of 75 to 80 kV.
I'm sorry, one more time. Is that going to be on the...
Well, it's not like that.
Oh, it's right there. Sorry.
Except for the 75.
Except for 75 kV. I'm just expanding my And the tube and the main housings has oil surrounding it. The purpose of the oil is for help insulations and thermal cushion because the production of heat generate a lot of
Production of X-rays.
The production of X-ray generate a lot of heat. So the oil help dissipate the heat more fast and more efficient. Any questions? So here it's the diagram of the metal housing, and within the metal housing are the X-ray tube. The only part where the useful beam should come out would be the port, interaction with the patient, and then the film. Any place where X-rays coming out would be radiations. And here's the animations. The tube housing is generally made of cast steel with lead lines surrounding it. As a precaution to protect any radiation. In 146, this it's on Mr. Fernandez. I will take out the tube and show you guys. I also special activity in this class. So we have a couple extra tubes inside that 1309, just laying around. And we have this. Just a cross section of the metal housing. Here we have the cathode anode within the envelope. Put it in the center. This will support the window. So it's coming out. And the other apparatus device. Okay, the envelope. I should change this slide. Glass envelope or metal envelope is mainly composed of Pyrex glass, Pyrex metal or metal.
Do you have a Pyrex metal?
Yeah, Pyrex. Yeah, the cookingware, Pyrex. That's what I think of Pyrex.
Pyrex is glass.
Within the envelope is a complete vacuum. There's no air molecule in it. The reason being is that when the electrons travel from the cathode side to the anode side, we want to straight projectile without any disruptions. If they interact with the air molecule, those electrons may move into different direction, causing the production of X-ray to be more inefficient. So within the envelope, which is a vacuum.
So how do they just suck the air out? Or?
I'm not quite sure how to do that. And again, oil surrounding the envelope because it's inside the particular metal housing, and the metal housing have oil all around it to absorb and dissipate heat. So here, so it's the envelopes inside, the yellow with the oil, electron, production X-ray, then coming out through the window. The arrow is pointing actually in the wrong direction because it's supposed to go from the cathode to the anode. All right, the parts of inside the envelope, the cathode side. The cathode side would be just a negative charge side of the X-ray tube. This is where we get the source of the electrons. To produce X-ray photons. The main component of the cathode side would be the filament and the focusing cup. Again, it is negatively charged since it's on the cathode side. And this is where thermal emission occur, too, from the filament. This is the picture of the cathode and anode. It is the focusing cup, and within the filament, and it's really close to the anode side, which is mainly made of a big disk, the tungsten disk. And the electron coming out from the cathode side through process of thermal emission, go at very rapid speed, and interacting at the anode side, the tungsten disk, and then with the electron interacting with the electron from the disk, that produces X-ray photons. And it's about an inch apart. Oh, yeah, the filament. Filament, this is where I mentioned thermal emission occurred. When we put the film through that and the filament, just like incandescent light bulb filament, but just more thicker and stronger and durable. When it starts to, the electrons flowing through, it starts to glow very hot. It then produces what we call space charge, which is just a cloud of electrons. As the space charge continues, these electrons will escape from the filament. The escaped electrons will be the projector electrons. It goes from the filament straight to the anode side at a very, very high speed. The filament is made of a metal called tungsten. Just like any filament, every time you use a light bulb, when we use a light, what happens to the filament?
Burns out.
It burns out and breaks. Same thing with X-ray. That's pretty much the number one cause of the tube failure is the vibrations and the brittle of the filament. Okay, the more we use it, the more thinner it gets, and the more brittle, and it breaks, and then we replace it. And which costs a couple $1,000 just to cost someone to change. There you go. In today's X-ray tube, there's usually two different size filaments. One's large and one's small. It's sometimes referred as a dual focusing tube. And the reason why we have two different size filament is mainly for different body parts and for resolution as well. The smaller filament generally give you more detail because of the beam is much closer to one another. With the smaller filament, however, you can only have certain setting of MA going through it. And generally, you can only have a setting of 200 MA and less. Anything more than that would cause a lot of wear and tear to the small filament. Some textbooks put down 300. I go by conservative, 200. And the larger filament is used mainly for bigger body parts, such as the abdomen, skull. Small filaments mainly used for like extremities, like foot, knee, hand. The benefit of using a larger filament is that it could withstand high heat, so we could use high MA station and longer exposure time as well. The downside of using a large filament that resolution does decrease by a little. I mean, from your eyes point of view, you can't really see it, but in the laboratory experiment, you could, if you take the same picture and do a quality test, there's a degrade in resolution. So sharpness does decrease, but it gives you higher long exposure. That's pretty much the difference between small and large filament. Small filament, very detailed, usually for small body parts. Large filaments, usually for bigger parts, such as abdomen. Any questions? Here's an image of your filaments, one large and one small. When we select, let's say, 400 MA stations, the focus bar selector will automatically switch from large to small. That's in the diagram when you look at it last week. There's two different currents. That's one you guys be aware of. One's filament current and one's tube current. Filament current flows through the generator from the filament and filament transformer delivered to the filament itself. Supported by a step-down transformer. And this is how we get our thermodynamic emissions. And the filament current is measured in amperes. Tube current will be electrons of current flowing across to the X-ray tube, from the cathode to the anode, through the process of thermodynamic emissions, where all those escape electrons. Tube current measured in milliamperes, MA. That's why when we do our technique selection, we measure our technique selection in terms of tube current, not so much as filament current. Changing MA selection to current would adjust the amount of current, so the current will adjust to give you that amount of MA selection. So that's the main difference between filament current and tube currents. Okay, the other part of the cathode side will be the focusing cup. This is generally made of molybdenum. I think I pronounced that right. Or nickel.
Molybdenum.
Molybdenum. The purpose of the focusing cup is to concentrate the amount of the electrons that are about to escape on the cathode side to the anode side at a very narrow path. Without the focusing cup, those electrons that are made in form of thermal emission will just go in every direction. So thermals is located inside the focusing cup. So electrons are negative, focusing are negative, so it causes all those electrons to come close together because they're trying to escape. So if it's negative, negative, so they have to all compress. As a compression, then they escape, just make a quick projectile over to the anode side. And then they produce useful X-ray beam coming out. Without it, all these electrons just fly in all directions. Does that make sense?
Mm-hmm.
Right. I think I'm going a bit too fast.
It's like almost the same thing as a collimator, right? Or like in a smaller form.
It's because they're both negatively charged, let's push them together.
Yeah.
And that's why it makes it tighter.
The collimation is just adjusting the light field, but it compresses together because it's like having two negatives. They have to go nowhere. So once they get so close to each other, once they reach out, it just goes straight.
Okay.
Okay, the anode side. This is the positive side of the X-ray tube. It's mainly made of big giant dust. And this is where X-ray photons are produced. So this is where we get the source of the X-rays. The X-ray photons. An anode side attract the incoming electrons from the cathode. After the interactions with the tungsten disk, it then produces X-ray photons. The anode or the disk itself can be a stationary disk, you will actually remember the disk sometime, or rotation anode, which is what we see normally commonly see in the hospital, the rotation disk. The normal materials on the anode side that support the disk would be made of the tungsten, which uses the top layer, supported by molybdenum, graphite, and copper.
What was that second one again?
Where's molybdenum? What is molybdenum? What is molly? Oh, never mind.
That was you, man. Where's your mind at? On the weekend or what?
Stagecoach Festival. Alright, let's move on. So here is a stationary disk. With the tungsten on top of the system embedded. So it's not working. So the problem with this is that all the heat is generated in one surface area as you produce the electron coming in. It's usually using very low X-ray exposure. Quite a few dental units has them because they don't make a lot of exposure. The rotating disk, the advantage of having a rotation disk is that the electrons coming from the cathode doesn't strike in one area. So it spread out all the heat in all over the surface. So it can withstand more heat and could produce more X-ray. And then support by copper. Stationary anode using dental X-ray as mentioned earlier, and some photo X-ray machines, where high tube current and power is not really required. With a stationary anode, it's generally produced what we call large focus spots. focal spot is where the beam's coming out. That's this point of X-ray photon is coming out.
Do I get them up? In a day or two.
A larger focus spot. With large focus spot, we get to low resolution because a larger focus that the beam is diverging, so it's spread out more. The more divergent is, the lower the resolution is. That's why focus spot. The focus spot is the point where X-ray is emitting. Larger focus, the larger divergent particle. Large divergent beam, lower resolution. And because heat is confined in a small area, since it's not spreading out to different areas.
So the stationary just have one large focal spot?
Yeah, because it's just one large because this doesn't have different angulations, whereas the other two we could put two different focus points because of the angulation of the disk. Rotating anode, again, it's made out of tungsten. We call it the tungsten disk, and it refers to the target because that's where the electrons strike the disk, the target. The rotating disk, rotating anode, can revolve around 3,400 to 10,000 revolutions per minute. The advantage of having a rotating anode disk is that heat dissipates over the different area, so to stand more heat. And the tungsten also itself is a very good conductor in terms of heat conductivity. It takes the heat and dissipates the heat really fast. The layers in the rotating anodes, the top layer is made of tungsten because that's the metal of choice to produce X-ray, to use for producing of X-ray. And then we have molybdenum, and then graphite, and then supported by copper. And usually the tungsten also mixed with other alloy too. Sometimes you see a tungsten uranium alloy. But the main component is tungsten.
Do you mean main alloy because it's on top and there's more of it?
Well, yeah, because it's the top layer. That's where the electron will interact with the tungsten electrons. And then that's where we produce the X-ray.
Is there more of it too though? Is it bigger, right?
The tungsten?
Yes.
Yeah, well, it's spread out over the entire disk.
And
The
it's
top
smaller.
layer is the tungsten. And then supported by the other
Mhm.
alloy. Have you had this? Okay, why tungsten? Well, because they have a high atomic number, which is number 74. This high atomic number is efficiency in terms of X-ray production. Another factor of using tungsten, besides it's readily available, is that it has a high melting point. As I mentioned, the production of X-ray generates a lot of heat. This high melting point for tungsten is about 3,400 degrees Celsius. And also have high heat conductivity, absorb the heat easily, and release the heat fast.